So the molar mass of a gas can be determined experimentally, and it's really not that difficult. We can even do it for things that are liquids at room temperature, provided that they're volatile, meaning they evaporate at a relatively low temperature. We're actually going to do this in lab. I think it's next week. So what you do to do this experimentally is you take a sample of this volatile liquid, you weigh it so that you know the mass, and then you heat it until it becomes a gas. When it's a gas, you're going to measure the temperature, the pressure, and the volume of the gas. From that information, you can calculate the number of moles of the gas. And then the molar mass is the mass of the gas in grams divided by the number of moles. So let's do an example. A sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. So I look at a problem like this, and the question part or the instruction is always very important. Find the molar mass. Then I ask myself, well, what is molar mass? It's grams per mole, right? So molar mass, which we sometimes abbreviate capital M, it's grams per mole. So that tells me what I need to look for. I need mass and I need number of moles. So I look in the problem. Well, what's this? 827 milligrams. I could convert that to grams, right? So is that going to be 827,000 grams or 0.827 grams? 0.827. So that's the mass. How many moles of gas? I can find it using which equation? PV equals nRT. So PIV-NERT, right? Ideal gas law. PV equals nRT. Okay, so 1.2829 times 0.270 divided by 0.08206 divided by 361.15 equals, and I'm getting a number of moles at 0.116. This is going to have 3 sig figs, and then 88, 2 extra digits, that many moles. Is that a reasonable number of moles? Yeah. The mass here is 827 milligrams. That's really small. And so we expect it to be a very small number of moles. Be careful when you're plugging this into your calculator that you don't accidentally multiply by 361 instead of dividing. So then I'm going to take that number of moles and put it into my equation up at the top, 0.11688 moles. So I've got 0.827 divided by 0.011688. I get 70.756. Units are grams per mole. 3 sig figs, that rounds to 70.8 grams per mole. Is that a reasonable molar mass? Yes, it is. I took the 827 milligrams and converted it to grams. I didn't show the conversion, but that's what we did. What if I got 0.7 grams per mole? Would that be reasonable? What's the smallest molar mass possible? Hydrogen. Hydrogen is a diatomic molecule, so its molar mass would be 2 grams per mole. You're not going to have anything smaller. So if it's less than 2, you did something wrong. And you also shouldn't end up with thousands, especially for a gas, because as a substance gets larger in molar mass, it tends to have a much higher boiling point, and so it's going to be hard to vaporize.
So it should never be less than 2 and higher than 1?
Well, the higher than is, there's no hard and fast line. But if you came up with like 1,000 grams per mole, or even like 500 for a gas, probably not. There are molecules that have masses that are like 1,000,000 grams per mole, but they're not going to be gases. Any questions?
What is the 1,000,000 grams per mole?
Oh, you can have like DNA as a molecule,
Oh,
God,
right?
that sounds too scary.
So that's really long. DNA is long enough that, it's large enough that you can actually see it. You can, if you unravel it, you can actually see a strand of DNA.
so it counts.
It's a molecule. It's a molecule. Let's do another example. This one's more like what you would actually do in lab. So an organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid, and fills, typo there, fills the flask with gas. She closes the flask and reweighs it. Her data is given below. Calculate the molar mass of the liquid. So here we have the mass of the flask and the mass of the flask with the gas in it. And then we've got our volume, our temperature, and our pressure. We need the molar mass of the liquid. So what's molar mass? Grams per mole. So molar mass is going to be grams divided by moles. Well, what's the mass?
Is it just the mass of the flask plus gas minus the mass of the flask?
Yeah, it'll be this number minus this number, because this is the flask with the gas in it, and this is just the flask. Some students just understand that, and other students kind of struggle with it. And I see that in your lab reports, when I'm like, oh, yeah, you calculated the molar mass of the flask. That's not helpful. So how do you think about this? I think of this as like weighing your puppy. So you've got this big puppy, and you need to give him some sort of medicine, right? You need to know how much he weighs. Are you going to be able to get a puppy to stand on the bathroom scale? No way. So how do you weigh the puppy?
Hold them.
You hold him. So you get on the scale holding the puppy. Now you've got the mass of yourself and the puppy. And then you put the puppy down, you weigh yourself again. And that's just you, and you subtract. The difference is the puppy. That's all we're doing here. You are the flask, the gas is the puppy. So if you put it in terms of that, then I think everybody's like, oh, yeah, I just have to subtract. Otherwise, it looks too sciencey, and then people freak out. Okay, so to calculate the mass here, I'm just subtracting these two numbers. I'm taking the flask with the gas in it, and I'm subtracting the mass of just the flask by itself. So I get 0.582 grams. So that's my mass, 0.582 grams. I need the number of moles of the gas, right? So like the previous problem we did, we're going to use the ideal gas law. N equals PV over RT. And so we need pressure, volume, temperature. In this problem, they're already listed out for us. But what do we need to do with these units? We need to convert them, because the ideal gas constant, 0.08206, you write that enough times and you just don't even have to try to memorize it. You can't help it. I couldn't forget that one if I tried. Liter, atmospheres, mole, Kelvin. Those are the units I need. So milliliters, I need to convert that to liters. So we've been talking about converting between like milligrams and grams or milliliters and liters by just moving the decimal point over 3 places. Fast and easy, but make sure you do it in the correct direction. So is it 0.213 milliliters or 213,000? 0.213. So that's the same as 0.213 liters. Liter is a bigger unit. The number should be smaller. Milliliters are small units of volume, and so I'm going to have a larger number. 100 degrees Celsius, I have to convert that to Kelvin. So that ends up being 373.15 Kelvin. Which digit should I underline as my last significant figure? I heard 3 and 1. The correct answer is the 1. It depends on the number, or the number of decimal places, really, in the original temperature. Here, this has been measured to the nearest tenth of a degree, so then I want to keep the tenths place in my converted temperature. So that I gave you kind of a simplified cheat for how to do sig figs with temperature conversions. This one, you can also just look at the rules for sig figs with adding, because we're adding here. Then 754 torr. So that's 1 atmosphere per 760 torr. Remember, torr and millimeters of mercury, exactly the same number. So 754 divided by 760. 0.992, 3 sig figs, 11 atmospheres. So I'm just going to put all of these into my equation. 0.99211 atmospheres times the volume, 0.213 liters, R 0.08206 liters, atmospheres per mole, Kelvin, and our temperature 373.15 Kelvin. So for the number of moles, I'm getting 0.0069012 moles. Make sure that that's the number that you get. If you're getting 960.9, you're not talking to your calculator correctly. So there's my number of moles. I'm going to stick it up here. I want grams per mole, so I take the grams and I divide by the moles. .582 divided by 0.0069012. And this result should also have 3 sig figs. So we end up with 84.3 grams per mole. Any questions? I want you to know how to follow the sig figs all the way through and do it correctly. But second best is to at least get in the ballpark of the right number of sig figs. You'll notice that a lot of these problems end up with 3 sig figs in the answer. Most problems that you're given are going to have 3 or 4 sig figs because of our starting numbers. So if you really suck at sig figs, go with 3 or 4. But be sure to write down a few extra and then round. Because if you realize, oh shoot, that wasn't nearly enough, you can go back here and you don't have to redo the whole calculation. And I really, really don't want you to over round as you're going along. Because if you round this to 1, that's going to mess things up. And the more times you do that, the more messed up your final answer gets.